So let's look at an example. In this case, we're going to have two different solutions. We're going to have 20% H2SO4, and we're going to take 2-pound mass of that, okay, at 60 degrees Fahrenheit, and we're going to mix it with 3-pound mass of 70% H2SO4 in water at 100 degrees Fahrenheit. And what I want to know is well, what's going to come out of this mixture, okay? I can tell you it's going to be 5 pounds mass, right? Just because I'm mixing acids and waters, the mass isn't going to change. But what's my percentage of H2SO4 in my final product? And what's my temperature of my final product? So if I do this adiabatically, then no heat is going to be transferred in or out, and so I can predict the final temperature. Or if I want to know if the final temperature needs to be 80 degrees Fahrenheit, how much heat transfer will be required. Let's begin by finding our given information here and marking it on the graph. So first I have one solution that's 20% H2SO4, which means it's along this line at 60 degrees Fahrenheit, so it's along this curve, meaning that that's my point 1. So enthalpy 1 looks like it's about negative 40 BTUs per pound mass. My other solution is 70% H2SO4. So it's along this line. It's 100 degrees C, or degrees Fahrenheit, excuse me. So this is going to be 0.2, and it appears that it's at about negative 114 BTUs per pound mass. Okay, and so the total enthalpy of my feed is going to be 2 pounds mass at negative 40 plus 3 pounds mass at negative 114. All of these are going to be in BTUs per pound mass times pound mass, so therefore BTUs. So negative 422 BTUs are how much I have in the system initially. Now I can also do a mass balance. So my material balance, if I do it a total material balance, I have 2 plus 3 equals 5 pound mass of my final product. And if I do H2SO4, I have 2 times 0.2 plus 3 times 0.7 equals 2.5. And so my product is 50% H2SO4. Okay, so my product is going to be 50% H2SO4. I know that, but then they've asked me a couple of different things about this. I can work the problem making a couple of different types of assumptions. So they first ask, if they mix it adiabatically, what's going to be the final temperature of the solution? So if you mix it adiabatically, it simply means that I remain on a curve where my total enthalpy is what would be predicted if I took negative 422 BTUs and divided by 5 pounds mass. And if I do that, then I end up with my enthalpy point being right here, which happens to be the straight line that connects the two original feeds and my product composition. Those intersect. And this could be demonstrated also using the lever principle. You're going to find that we love the lever principle in chemical engineering. But so this is going to be my point, and I can use that to estimate that if I mix these adiabatically, the final temperature is going to be about 112 degrees Fahrenheit. Okay. Now the other question is, what if I needed to have the final product exit the system at 80 degrees Fahrenheit? How much cooling do I need to provide? Well, that's a little easier because I'm going to find where 80 degrees Fahrenheit intersects with my 50% solution, which is right there. The enthalpy is going to be negative 104. Okay, I have 5 pounds of product. And so I simply need to find the enthalpy of the final product and subtract to get the answer. Okay, so negative 104 times 5, negative 520 BTUs. Then subtract from that the negative 422 BTUs of the original feed. And so therefore I need to remove 98 BTUs to reach 80 degrees Fahrenheit. So this concludes this little lesson. Again, there are other video lessons that can be very helpful to you, and they work a couple of examples in the textbook. Also, be sure to look at the sodium hydroxide and the HCl data provided in your textbook.